Hello everyone, welcome to the lecture. Myself Devananda Rao, working as Associate Professor in the Department of CSC, MLR Institute of Technology, Hyderabad. Today's topic is Peephole optimization in the context of code optimization. A statement by statement code generations strategy often produce target code that contains redundant instructions and suboptimal constructs. Here, the code may contain redundant instruction, that is, the statements may be repeated. A simple but effective technique for improving the target code is Peephole optimization. Peephole optimization is the code optimization technique. It will be used to optimize the code. A method for trying to improving the performance of the target program by examining a short sequence of target instructions called Peephole. Here a Peephole is a small window moving on the source code, so that the sequence of target instructions and replacing these instructions by a shorter and faster sequence whenever possible. So, here we have code having some instructions are called costly instructions. We can replace those costly instructions by cheaper and faster sequence of instructions, so that we can improve the code. The Peephole is a small moving window on the target program. We shall give the following examples of program transformations that are characteristics of Peephole optimizations. We have the 5 techniques of Peephole optimization. First one is redundant instruction eliminations, unreachable code, flow of control optimizations, algebraic simplifications and use of machine idioms. First one, redundant instruction elimination. If we see the instruction sequence like move R0 comma A, second instruction move A comma R0. A is a variable, R0 is a register. So, the first instruction tells about moving the value of R0 to a variable A. R0 is a register containing value, that value is moving to a variable A. Second instructions, once again A is the value of A is moving to register R0. So that we can delete this instruction 2, because whenever 2 is executed, one will ensure that the value of A is already available in R0. So, whenever you try to execute the second instructions, first instructions ensure that the value of A is already available in R0, so that we can eliminate this instruction, because this is a redundant instruction. So, that redundant instruction elimination. Second one, unreachable code. Unreachable code. See, x is declared and initialized with the value 0. X is initialized with the value 0. Next instruction, if x is equals to 1, if x is equals to 1, here we are checking the condition, the value of x. Here x is 0. If x is equals to 1, then this block will be executed. So that x will never be a 1, because already x is previously initialized to 0. So that this instruction, if x is equals to 1, is unreachable code, so that we can eliminate. So, for this code we can write the intermediate code. So, intermediate code will be like this: x is equals to 0. If x is equal to 0, if x is equals to 1, go to L1, where L1 is a label, there a statement is there, that is x is equals to A is equals to B. Otherwise, go to L2. X is equals to 0. If x is not, in another way you can write it, if x is equals to 0, then if x is not equals to 1, directly go to label 2, otherwise A is equals to B. Flow of control optimizations. The unnecessary jumps can be eliminated in either the intermediate code or the target code by the following types of Peephole optimizations. We can replace the jump sequences. See, unnecessary jumps can be eliminated. See, we are unnecessarily jumping from L1, go to, from here, from this location, from go to L1, that means control go to label L1. There once again another go to is there, go to L2, control goes to label L2, there the statement will be executed, A is equals to B. So, this is unnecessary jump, that will be eliminated. So, directly write go to L2, there a statement containing A is equals to B. Next, algebraic simplifications. X is equals to x plus 0 or x is equals to x star 1. So, that x is equals to x plus 0, adding 0 to x, that will not change the value of x. This is we can eliminate this type of express algebraic simplification, so that no need to write this type of instructions. X is equal to x plus, adding 0 to x will not change the value of x. Another, x is equal to x star 1, multiplying 1 with x will not change the value of x. So that those instructions we can eliminate, so that we can optimize the code. Then reduction in strength. Reduction in strength replaces expensive operations by equivalent cheaper ones on the target machine. For example, x square is invariably cheaper to implement as x star x, that as a call to an exponentiation routine. So implementing x square is costlier. So if you write x star x, it will take less time to compile, so that the strength will be reduced. Use of machine idioms. The target machine may have hardware instructions to implement certain specific operations effectively. So the target machine sometimes having hardware instructions to implement certain specific operations. For example, some machines have auto increment and auto decrement addressing modes. These add or subtract one from an operand before or after using its value. See, for example, I is equals to I plus 1. That meaning is I value is incremented by 1. Then I is equals to I minus 1. That is I decremented by 1. Instead of writing these instructions, we can use hardware instructions. That hardware instructions are auto increment and auto decrement. Auto increment is INC I. Auto decrement means DCR I. INC I means the value of I will be incremented by 1. DCR I means the value of I is decremented by 1. The use of these modes greatly improves the quality of code when pushing or popping a stack as an parameter passing. So in these applications we can use these modes. These modes can also be used in code for statements like this is the example where we can use auto increment, auto decrement of hardware instructions in some target machines. This is the use of machine idioms. Thank you.